We'll just wait for a few more minutes for other people to join.
Yeah, that's great.
We're already 5 minutes in. I guess we'll get started while other people join. First, just a quick reminder, if you haven't done so, please add your name to the meeting minutes attendee list to record the attendance. Otherwise, we'll go ahead and get started. So today we have thank you, Pushka, to join us again to continue to talk about disk integrity, disk identity and integrity for confidential compute. Thank you, Pushka. Can you go ahead and get started?
All right. I will just share my screen to let me know if you can see it. Can you guys see my screen?
Yeah,
Yes.
we can see it.
All right, perfect. Let me go back. Okay. So the last iteration we had, right, early this year, we kind of described the problem statement, right? So maybe I'll quickly go through the problem statement in a few minutes, right? And then if anybody has any questions, they can ask, and then we'll jump right into the solutioning here. Um, so let we talk about the scenario, right? The scenario was essentially that we have uh, we have disks, in this case specifically operating system disks, though eventually we can generalize to any sort of primitive, right? And the risk disks have read write state, right? Sometimes it's a read write only disk, right? It's a read write disk, a standard disk attached to a confidential VM or a TE, or it could be a disk which is acting as a scratch on top of read only disk, right? But the state needs to be persisted or at least maintained, and its integrity maintained during the runtime of the confidential VM. Um, so what we're trying to do is establish, you know, who generated a particular or who owns the disk. In the case of OS, who owns the OS image, right? Can we establish a cryptographic identity for that OS disk, right? If we can have a cryptographic identity, then we can run policies on top, right? Mount policies, launch policies, right? Technically, can we abstract it to a cryptographic identity to any read-write disk, right? In the past, we've had folks in security in our company who have who have posed an open problem, which is we can run a lot of policies on different kinds of aspects, but when it comes to read-write disk, how to define a cryptographic identity for a read-write disk, and how do you bind it to a policy, right? And if you can't do the former, it's hard to do the latter, right? And so the best we could do is identify if there should be a disk or not, right? But not if this disk is a valid disk or a acceptable disk to be included within the TE environment. And so those are some of the aspects which we want to cover, right? Can we assert the identity of the disk across read write, right? So if it's a persisted VM, a VM which maintained its lifetime across multiple instances, even across reboots, can we maintain the identity of the read write disk and assert it during the lifetime and ensure that its integrity is intact, right? And like I said before, can we generalize it to any kind of disk, OS disk, data disk, app disks, any form of disk if we attach to a TE environment, right? We are looking for collaborators and partners. I do want to call out that after the last problem statement description, there are a couple of folks who reached out to me, right? I'm yet to set up an official conversation with them on the side because I had some legal things I needed to get sorted out. But now that is sorted out, and so folks who had reached out to me in the past expect me to set up a forum for a discussion here. And then others who want to join in, please do reach out through email or through LinkedIn, right? We're happy to collaborate. So again, I'm going to run through these next few slides and very quickly. If you have any questions, just stop me, right? So basically, we have already talked about confidential VMs, right? Confidential VMs have a boot integrity established, bound to some attested hardware TPM. In our implementation, that runs inside the confidential boundary, and the measurement of the initial boot components, that's the UFI and boot integrity. What we are concerned about is how can we establish integrity of the OS image, right, or disk, which is attached on top. If you would like to have more discussions around Azure's implementation of the VTPM inside the confidential VM, there's obviously the link here. That was a talk given by Mike Stunes in the same forum last year. Supply chain becomes the most interesting aspect, or amongst the most interesting aspect for us, right? So if a disk is moving from publisher through a pipeline, through storage, and then being used for disks, all of these are vectors of attack. For read-only disks, there has been some established process. You can have a read-only disk. You can sign the read. You can establish a root hash for a read-only disk, have it signed using a particular hash, and maintain the integrity across end-to-end. There are also other implementations to maintain integrity of state if it is unmodified in this entire pipeline. But then we also would like to make sure that that integrity state is maintained right away, all the way to the CVM boot, and be able to attest that particular integrity posture, right? And so our requirement is not just to maintain the integrity and keep it intact, but to also make sure that when the CVM boots, it can actually attest to the fact that the integrity was maintained and the image came from the trusted publisher, right? Some of the solutions when the confidential VM has been purely ephemeral, right? So confidential containers or different forms of confidential VMs where the read write disk is a scratch disk, right? It's thrown away across reboots. What we have done is we have had a read only disk, used implementations like DM Verity to establish a Merkle and a root hash. You can sign that root hash and get some form of identity associated with that particular disk, and then maintain that across reboot. I would argue that during that initial run, the one runtime as well, the scratch disk integrity has been lackluster, right? Like as of right now, the scratch disk, even if you're maintaining the state across, not maintaining the state across reboots, the state which we do maintain, right? You can cryptograph, you can encrypt it, you can do block level integrity, but there is no equivalent of block device level integrity or file system level integrity, right? Like we have with DM Verity for the read write disk, right? And so that's a glaring issue even for this ephemeral scenario. This obviously becomes much more concerning for the persistent scenarios where we want to have the confidential VM maintain the read write state, right, of its disks across reboots and still be able to reason about the integrity of the state as you go from one reboot to another, right? Um, the other problems which we are trying to solve, right, is specifically for our confidential VMs, is to make sure that we create this strong binding between the OS state which we are booting with and the firmware state which we rely upon. The firmware state includes the UFI and TPM state. This is more to do with the fact that customers or the workloads which want to leverage the virtual TPM should be able to reliably leverage it, and we should never have a state where we can roll back just the firmware state without rolling back the OS state, or only roll back the OS state without rolling back the firmware state, right? And so that's the requirement which we are adhering to, right? And so this diagram kind of gives portrays the ideal state we want to be in, right? We boot with the original state at T0 for OS and UFI TPM state. If you across reboots, so from T0 to T1 to T2 to T3, we want to maintain a continuous chain of integrity, right? So we should be able to reason about the fact that when we are at state 3, that state originated all the way back from state 0, and at OS state 3 at T3, we should still be able to attest that we booted from the original OS state 0, right? Um, the binding aspect which I called out earlier is also defined in the statement below, which basically says that the OS state and the firmware state have a need to establish a cryptographic binding such that we can, we cannot swap or roll back any individual state without detection, right? So basically, you can't do a swap of the OS state to some other random OS state or even a previous version of the OS state. It has to be in line with the TPM state. If rollbacks are to be allowed, they are in a collective, right? So you can take the state 3 for OS, UFI, and TPM and roll back all the way to state 2. That rollback can also technically be protected, but that's not part of today's discussion. Do keep in mind that if we establish this binding, then if we are able to prevent the rollback of the UFI state or the platform state from UFI TPM from state 3 to state 2, we can also prevent the OS state rollback from OS state 3 to 2, right? Because of the strong cryptographic binding, right? And that's the approach we would offer in case that need comes up, right? And so this is essentially everything which I just mentioned, relisted, which is we need to establish the OS disk identity, who published the image, right? And it should include identity should include things like hash, attributes, and signer. We need runtime integrity, right? Which is we want to protect against external disk tampering, right? And maintain the continuous ordered integrity chain, right, for the CVM across the first boot and across reboots, right? We want to be able to obviously attest the fact that we are booting with a known OS disk and with the known OS image, and we want to be able to do that across boot and reboot, right? And then the final requirement which I mentioned, which is we want to make sure there's a binding, right? So can we use some of these cryptographic primitives we have established to create a binding between firmware and TPM state, so that we can help reason about them as well, right? I'm going to start going into solutions. Are there any specific questions on the problem statement?
Yeah, I think I mentioned this last time, but I mean, disk swap is normally managed by the host, yet this identity is going into the CVM. So I'm assuming that those kind of disk swap operations are completely independent of what's being proposed here. So, in other words, the CVM wouldn't use this identity to try to block the host from doing whatever it needs to do for memory management.
So what we're saying here is the because the host is untrusted, right? The host, if it attempts to do a malicious disk swap, right, which could mean it took a the confidential VM booted with a particular OS disk, and then across during that runtime or during a reboot event, the host environment swaps out the disk with a completely random malicious disk, right? Or if the host tries to roll back the OS disk to a previous version of the OS disk, right? Or the OS tries to even like swap out blocks of OS disks, right? Like blocks, or roll back individual blocks. All of those are potentially malicious actions which the host can perform. And what you would like to do is for CVM to be able to detect against those, and then guarantee that if an OS disk or a disk is accepted within the TE boundary, it has to adhere to the policy of the confidential environment, right? And so functionally, the hosting environment can perform all these operations. What we want to guarantee is that in terms of security properties, the confidential VM can protect itself against any of these class of attacks.
The the type of attack you described, though, I mean, if you look at like a CVM um, that maybe attests itself upon, validates its attestation upon launch. What you described as a runtime attack, where the disk is actually swapped um, after the CVM has been launched. So the CVM would have to actually periodically reattest in order to detect that detect what you just described. Um, and even then, when it detects it, it would still need a way of blocking the swap operations. So this, um, which which is maybe not even desirable, right? Because the CVM doesn't have a full view of the entire system memory. Host does.
So I'm not sure uh, why the memory came into the picture, right? But yeah, you are right around the disk aspect of things, right? So
Well,
uh,
the memory comes into the picture because why is the host doing a disk swap in the first place? Because it's running into a system memory issue. So it's so it's selectively moving CVM pages back and forth between the disk. So that's why the memory comes into play.
so I'm not specifically talking about memory paging here, right? Like
Yeah,
I'm
but
talking about.
it's going to a disk. So you are, right? I mean, you should. I mean, what are the why are page swap operations happening? So page swap operations are happening because we're trying to relieve memory pressures on the SoC. Memories, so
So,
yeah, so CVM pages are being copied to disk.
so let me take an example since you talked about memory paging, right? So, and
Yeah.
I will use the example of a CVM which is functioning today. So there is a CVM which works in a cloud environment. It has a temp disk, right? The temp disk is the enables encryption to make sure that the contents of the disk which are written into the disk are encrypted. The temp disk is encrypted with a key which is bound to the TE, right? And it can be used for swapping out memory pages, the page, just for from the paging scenario, right? If the hosting environment can take that encrypted disk and then swap it, let's say an encrypted disk which was protected using de-encrypt or BitLocker, and swap it with another disk which is unencrypted, which doesn't have any encryption enabled, and if the page writes end up in that particular disk, right, we are now expose ourselves to a potential attack, right?
Yeah, I
And so
agree that the attack is that I agree with the attack you said, but I'm asking how how does the CVM protect itself in that case? Because it's already probably attested once
yeah,
when
I'll talk
upon
about that.
launch. Yeah.
I'll talk about it. Yeah.
Okay.
And I won't put it as reattestation. I would just put it as it has to be reason about the integrity of the system every time it tries to mount, and every time it tries to write, it has to maintain integrity. So yeah, I'll talk about that. Let's maybe in a couple of
Yeah.
slides.
Yeah. Please go ahead and continue. Thank you.
Yeah, yeah. Um, any other questions? Okay, Fred, I'll jump into the solution, and then we can come back to the discussion, right? So, I mean, we looked at bunch of existing solutions which people have implemented. A lot of it around, again, the ephemeral scenarios, or they're being used for the persistent scenarios, but not getting all the properties which we desire, right? So, if you look at the standard layered architecture we see in multiple implementations, we create a layering using overlay FS or DM snapshot. Uh, we do see some benefits of using DM snapshot in terms of compatibility, right? For certain scenarios, especially for standardized VMs, like generalized VMs. Um, but so DM snapshot is used for layering. There is DM Verity, which is a bunch of read-only layers at the bottom, and then there is the read-write disk at the top, which is typically encrypted using let's say de-encrypt or BitLocker, and then there is integrity protection involved, right? Bound to some HMAC key or equivalent, right? But this is at the block level, right? So that we have block level integrity protection, and essentially bound to the key, typically the same key which is being used for encryption, right? If you're using de-encrypt and DM integrity together, right? So this is the sort of the lay of the land we found, right? And standard usage for different sort of confidential computing implementations, right? For the area we found lacking was the read-write integrity, right? So there was no solution which was catering towards the block device level integrity, right? To prevent block swaps and block rollback attacks, right? Um, uh, so uh, so an integrity solution which can cover the entire block device or the entire file system is what we would ideally like to have, right? The other benefit of that being, if it's a integrity solution over the entire block device, it can be used to create a identity for that entire block device, right? Even if it's read, right? Then the other aspect was we didn't find any standardized scheme to create this integrity chain across edits and mounts, right? So read-only disk, you have one Merkle root hash, no changes being made, everything seems fine, right? But now the read-write layer on top of it, if it is being maintained through that one runtime or across reboots, right, and edits are being made, there is no real identity associated with it. There is no real guarantees around the edits and mount, and especially across reboots, there are no guarantees at all, which is why many of the scenarios rely on ephemeral scenarios where they say across reboots, the read-write layer, which is a scratch space, is dropped, right? That does work for a lot of scenarios, including containers and other aspects, but does not across standardized VMs, right? So I'll jump right into our solution, right? And we started investments in read-write Merkles, right, and implementations of the same, right? So read-write Merkles are interesting. They're not as widely being used as at least I would hope for, right, as of right now. But the read-write Merkle allows a representation of the read-write disk using a single root hash, right? What it basically means is just like DM Verity, right? But now for a read-write disk, right? There obviously the implementations have to take into account a lot of performance considerations and other aspects. But essentially, at the end of the day, think of it: there's a Merkle or there's a collection of Merkles. At the end, there is one root hash which represents a given state for a read-write disk. The Merkle root hash covers both data and metadata, right? But there is something which is interesting here, which is unlike read-only variants, right, such as DM Verity, obviously for a read-write disk, we'll expect updates, right? So there can be update to a data or metadata, and that will change the root hash, right? If you think about it, as soon as you take a read-write disk and just mount it, that actually changes metadata, which means it will change the root hash of the read-write Merkle, right? And so while the read-write Merkle can be a representation of the integrity state and the state of the entire disk at a point in time, it will keep changing with a period of time, and that's essentially becomes the interesting aspect of how to actually leverage read-write Merkle to establish different integrity chains. We have read-write Merkle implementations. We've started looking at ZFS and ButterFS. ZFS is not upstream into the kernel, but is widely used for some production scenarios, right? Obviously, we are really interested in single disk sort of solutions, and there maybe even ButterFS might be useful. For Windows, we have ReFS, right, which is a file system which is supported in Windows. And starting Windows Server 2025, we do offer a ReFS which leverages SHA-256. A lot of our initial sort of dev investments we have put in is with ReFS, though we are now jumping into having a Linux equivalent solution. So everything which I've described here, or describe in the next slide, we have working for one solution, right? We are looking at adding the same for our, the Linux pipeline and Linux disks for that class of customers. So now we already said we have a read-write Merkle, but the root hash keeps changing. So how do we really leverage it, right? First thing, let's talk about what does the read-write Merkle help us help establish, right? So it can give us a initial identity of the read-only and read-write collective, right? If I look at the typical ephemeral scenario, we have a read-only Merkle hash, we have a read-write Merkle hash, but the read-write Merkle hash will be initialized as empty, right? That's what the standard ephemeral scenario is doing, right? In the case of ephemeral, after every reboot, the read-write the state is completely dropped, and the read-write Merkle essentially gets initialized to empty again, right? But what the read-write Merkle hash does is, if we can maintain the continuity across writes, and we can guarantee that all writes are authorized, right? So think of it as the disks is moving from state 0 to state 1 and state 2. If we can now, instead of state 0 and state 1, which represents the entire disk, the entire disk state can be represented by this Merkle hash, right? So we have a H0, H1, and H2. If you can create some cryptographic binding between these H0, H1, and H2, we can create an integrity chain, right? That's the sort of a principle we want to follow, right? But again, for initial disk identity, it's the read-only Merkle hash and read-write Merkle hash, right, which represents the identity. Now, the read-write Merkle hash, the read-write disk need not be empty, right? It could have actually had some state, right, which could have been then signed by some trusted authority, right? And so we could have a read-only Merkle hash, which represents some state coming from a trusted authority. Read-write Merkle hash, which is the read-write state, which is coming from some trusted authority. And technically, that model also works, even though in practice, I would expect that everybody would squash the read-writes, scratch space into the read-only, and then maintain this one Merkle, right? But you can also know how to do the flip, which is for any scenarios which want to just read with read-write disks, right? We can just maintain one Merkle, read-write Merkle hash, where the read-write hash represents, should represent a trusted value or needs to be signed by a trusted authority, right? And so again, as the disk mounts and as the disk goes through edits, the hash would change, right? But the first time it mounts, we know exactly what the read-write hash is, and if it matches an endorsement from a trusted authority, then we know exactly where that disk came from, right? And that's the property we would like to leverage. So if we only have a read-write Merkle hash, there is no read-only layer involved. There is no layering involved. It's just one read-write disk, right? Could be an OS disk, app disk, data disk, temp disk, any of the scenarios, right? Now, if you want to then think about the runtime integrity, which is integrity across the first boot, right? Or the first time we mount that particular disk, right? What we need to do is the runtime integrity of the entire file system or the block device is covered by the read-write Merkle, which means the Merkle root hash represents the entire content. The Merkle root hash, if it's signed by or authorized by a trusted authority, if it's endorsed by a trusted authority, then it's trusted, right? That's one property we would like to leverage, right? And then at any point of time, if we mount the particular disk, we should verify which trusted authority it came from, and then any edits we create, right, or any especially before we unmount, right, but any edits in general if we create, we should start signing those edits such that the next entity in the trusted chain can also verify, right? So every time we mount, we have to verify the root hash, whether it's trusted, and then every time we update the root hash, if you're signing it, then the next authority in the pipeline can always verify if it's trusted or not, right? And so to give an illustration example of this with the OS publishing pipeline, right? Now imagine we only have a read-write disk, but a read-write disk which supports read-write Merkle. There is no read-only disk or anything else involved. The image publisher generates the disk, but it is endorsed by the image publisher, which basically means uh, before unmount, the disk is prepared, and then the root hash which currently exists for that read-write disk is signed or endorsed, right? And then there's a corresponding endorsement which is packaged with that particular disk. That endorsement could be a quorum, could be a signature and a certificate, what have you, right? And so that is what is published by the initial publisher. Again, remember this is a read-write disk with the read-write Merkle. At any point in the image publishing pipeline, right, the Merkle and the root hash and the endorsement remains intact. At any point, if an entity wants to modify contents, right, so if it wants to customize the disk for some reason in the pipeline, it is welcome to do so. If it is doing so, it should always verify the source of the image. So the image is coming from a trusted source. In this case, let's say Windows, RHEL, Canonical, the image publisher. Then it should modify the image to its desired, right? Maybe it's a ISV which is customizing a particular image, right? And then after the image has been customized, it should do the same thing which the publisher did, which is essentially re-sign or endorse the image, right, with a different signature, right? Obviously, if the pipeline is just storing the image and not making any changes, the signature need not be changed or updated, right? And obviously, if any entity tries to any untrusted entity tries to modify any disk content, right, that will be detected at boot, right? Either the root hash would be different, right, or there will be Merkle issues, in which case disk reads can actually block or bug check, right? And now, when the CVM confidential VM boots with that image for the first time, right? At first time, it knows the identity and the integrity because it starts the first hash which is presented during the mount represents the identity and integrity of the image, right? And so the Merkle root hash has to be equal to the certified endorsed hash which came from the publisher, right? And if so, all that information is now available to the CVM in that first boot, right? And it can technically add contents of that, the claims from within that particular endorsement, say in the TCG log, right? So we are talking about the pre-boot components. This is the UFI boot manager, things which are helping mount and bring in the OS disk, right, are able to now ensure that the TCG log represents the initial set of measurements, right? But in this entire process, at least in our current implementation, we are able to also maintain an audit trail. So every time an entity in the pipeline resigns the disk, right, so makes modifications and resigns the disk, if it did mount it in a manner where it was already the root hash was already signed, we will maintain the entire audit trail of all the signers, right, which were verified during the last mount, right? And so in this particular case, you can only attest and reason about the last entity which modified and signed it. But at least if you want to audit, if you trust the last signer, you can also verify what it verified, right? And all that information will be, we leave breadcrumbs as part of the read-write Merkle within the disk itself for people to audit, right? And so to call out what we just went through, right? So publisher generates an image with some known root hash, and it generates an endorsement about this root hash. Any entity in the pipeline can modify the content of the image, right? As long as it verifies the source disk, right? It receives before it starts modifying it, right? And then it endorses the disk itself after modification, right? And then the CVM at that first boot is able to verify that Merkle root hash matches the latest endorsement, right? So it can actually say that whether it came from the publisher or whether it was modified by ISV, and that endorsement can be captured, and the claims from within that endorsement can be reflected into the CVM attestation, include, for example, in the TCG log. Right. So I'll stop there for a second. Are there any questions on this? Okay. Feel free to ask more questions if you have any. But yeah, I wanted to stress upon the pattern which you observed, which is at when you mount, you verify the source of the disk, right? Then when you make modifications, um, and especially if you unmount, you sign before you actually complete, right? This is the pattern we also want to now start exploring for runtime, right? So now CVM has booted for the first time. It is able to endorse that this particular element came, let's say, from, in this case, from an ISV, right?
Yeah, Pushkar, it might be nice to actually see how those steps occur with respect to the power on sequence on a on a host CPU host CPU based SoC. So if you go back, right, the CVM launch may occur after the after a cold boot, but the identity of the disk may be obtained at cold boot. So you may, in that case, you have a possible time of use in that case. And the reason the CVM may only launch, may launch during runtime of the SoC is because the operating system has to boot first, and the CVM may only be launched on demand. Um, so
Yeah. So
yeah,
the model we have is, if you have a disk, and if that disk is mounted anywhere other than the untrusted authority, you break the integrity chain, right? So in our implementation, what we're basically saying is, you have the disk in its raw blob form, you can maintain anywhere, the host can actually reference it, right? But when it is mounted, it needs to be mounted only in the trusted environment, in this case a CVM, and only then the integrity is maintained, right? If the
so
if you
so
mount the OS any other scenario, the Merkle root hash changes, and the endorsement no longer applies to that disk.
okay, so this is pretty important. So you're saying at cold boot, all the CVMs that are going to be running on the machine need to be launched, so they could be part of that. So the Merkle hash with respect to the memory stored on that disk can be verified. Is that
The OS
correct?
disk, the OS disk has to be mounted in the CVM, and only the CVM. If it's mounted anywhere else which is untrusted, any other VM or CVM or any other entity where it's untrusted, then your CVM won't be able to write
Okay, okay.
anything.
So we mixed up OS here. So I'm talking about the hypervisor. Hypervisor is clearly untrusted and outside of the
Yes.
outside of the CVM security boundary. So that's the operating system I'm talking about. That is the one which actually launches and tears down CVMs. If you go back to I can map this back to the S&P model, but I think you're already familiar with that.
Yeah.
So yeah, so in other words, the CVMs will be the CVMs like in what we call an S&P and S&P guest will be launched after sometime during runtime, right?
Yes.
So I'm asking, is the disk identity and integrity obtained when the CVM is launched, or is it obtained during cold boot?
So I don't want to call it, every time I mention OS here, I mean the guest OS, right?
Uh,
I'm not talking about the hypervisor, I'm not talking about the host platform at all. Technically, what we have built, we can separately use for operating system on the host environment as well. But all the examples and everything I'm talking about here is around the guest OS for the CVM, right? So the hypervisor is out of ECB. The hypervisor disk is not what we are focused on right now in this discussion, even though I'm happy to discuss
Okay,
that.
but that means that if you obtained image with identity integrity, if you obtained that at cold boot time, if that, or I should say if that was obtained at cold boot time, the CVM will get a stale measurement because the CVM is going to be launched at runtime and we don't know when, right? So that's the
So,
yeah.
so it's as long as that disk was not mounted anywhere, we are fine, right? The disk is not expected to be mounted in the untrusted hosting environment. The disk is not to be mounted in any other environment which is unknown to the CVM. It that and again, I'm talking about the guest OS disk, right? The guest OS disk, in this case, these are
Okay.
VHDs, right? Virtual disks, right? These guest OS disks need to be mounted only to the machine to which it is supposed to be bound to and trusted. If you mount them anywhere else, yeah, you break the chain,
Okay.
right?
So would it be fair to say that there's a disk partition that is associated with the CVM, and it's only mounted to the CVM when that CVM launches? Is that correct? That,
Yes,
okay.
and
Okay.
I think think of the OS disk as the OS disk could be remote in a remote storage, right?
Okay.
Which is typically for cloud environments. You're right. It could even be a local disk, or a temp disk, or a VM specific disk. But this particular disk fragment is signed, right? Its image has been is signed and created, and it is only being attached to that particular VM, right? I would for sake of simplicity, I would just say these are all VHDs, right? So you can have a VHD which is stored locally, or VHD which is stored remotely, right? VHDs are equivalent, like virtual hard disks, right? And the virtual hard disk is endorsed by by the publisher or the ISV, and is to be only mounted in a trusted environment, because a mount in an untrusted environment may mean that some changes have occurred, and also we lose the binding to the endorsement.
Okay. All right. Thanks. Appreciate it.
Yeah, but I
Does
think that's right. I think I will call out some concepts around VHDs and stuff next time. We do have implementations of these which we are exploring for bare metal scenarios, like the host environment scenarios as well. So if you think that's interesting, I'm happy to discuss offline. Yeah.
does
Okay.
the
So
VH
sorry, go ahead.
sorry, does the VHD carry the signature and certificate, or does the OS or CVM
So
know that up front?
So in our implementation, we have it all packaged in the VHD, right? So we have the VHD have additional blocks which represent the endorsements and the signatures associated with the particular Merkle, which represents the entire disk. But that's not a architectural requirement. That was just functionally made it much more simpler for us to operate and manage this, right? Like now we already have publishers publish VSDs. Now they can publish, quote unquote, signed or endorsed VSDs, right? And the entire endorsement, everything is packaged within that particular VSD, and we can have tools to extract it for auditing or writing policies and other stuff. So right now, our implementation, we package everything within.
But this certificate that you have here, how is it trusted by the OS if it's all packaged together?
Yeah, so the OS we can do two forms, right? One is this confidential VM. When it boots, it can either bind to the OS it has launched with, right? And then include that in the TCG log. And now it has to, on every reboot, keep mentioning that in the TCG log. That's one way to go about it. The other is the confidential VM can have a launch policy, right? The launch policy says that I will only boot with images published by this ISV with the minimum SVN number, or I will only boot with Windows images published after June 2025, right? So we can have
Mhm.
both sort of forms. Um, but the simplest form has been there is no launch policy, but then the identity of the image is inherited by the confidential VM and is included as part of its attestation, right? So the TCG log entry would have an entry which says this is the OS identity I booted with, and that OS identity has to be that the same identity has to be reflected across every reboot, right, for that particular CV.
Okay. It's a custom TCG event log entry, or you used the kernel command line grub stuff
We
that exists already?
we have created a custom TCG event right now. Even though we are happy to discuss if you think that should be something which is different. I think as we go towards launch policies, we can start standardizing it a little bit more. As of right now, it's a custom TCG log.
Okay.
So let me now go through the same sort of flow, but now across a CVM's lifetime, right? So now CVM has booted. We have booted with the first boot, right? We have got a Merkle root hash, right? Certified endorsed hash. This is where we left off at the end in the OS publishing pipeline booting, right? So first boot, we have the state. We know it came from a known publisher. We trust the image. We can reflect in TCG log, right? Or verified against the launch policy, right? Now what do we do, right? Like because when the CVM boots, it will start making edits, right? It will start making changes, and eventually it will also reboot. We also want to support reboot, right? We essentially try to follow a similar scheme, right? Where we basically say that the TCB components here, which is in this case everything protected by boot integrity, right? So in our case, we have a virtual TPM, we have a UFI, we have boot manager, right? These components, they are able to generate some HMAC key, right? So this HMAC key, the sealed, this HMAC key is protected using the boot integrity. Think of this HMAC key as representing the boot integrity of the system, right? If the boot integrity degrades, the HMAC key essentially vanishes, right? The other thing which the HMAC key is as part of its KDF, we mix in the original image identity, right? So image identity which we observed at first boot, which came from the publisher, we mixed in those values as part of its KDF. So when we talk about the HMAC key, which is generated by the trusted system, it represents a trusted system and it represents the identity of the original image, right? The endorsement which was bound to the original image, right? Now that we have this particular HMAC key, we essentially say that any update to the Merkle root, right, we sign using this HMAC, right? And so think of it as every time post boot and post establishment of this HMAC key, every write we are pushing out, right, in our read write Merkle implementation actually gets signed using this HMAC, right? Now, immediately when I mentioned this, people ask questions around performance and other aspects, right? So such as to call out, at least in our practice and our Merkle implementation, what we have found is a lot of cost is spent in actually the Merkle root hash establishment and the walking of the chain, and one additional HMAC signing has not really negatively impacted our performance. A lot of our sort of optimizations in our read write Merkle is all around how we maintain and write to the disk and how we walk the chain, which is where the biggest performance bottlenecks are, right? If there are questions on performance, we can also talk about that, right? But essentially, think of it as everything which is written is now HMAC signed, right? Now, this should look very similar to what we talked about in the previous slide, where we have the entire integrity chain, which is anything in the pipeline. If it modifies something, it signs it, right? And so what that basically means for us is any updates in this Merkle are now signed using this HMAC owned by the platform, right? Now, this platform represents the trusted authority, which is making modifications and signing, right? The benefit of that being that across reboot as well, if it's the same trusted platform and the same trusted platform is able to generate the same HMAC using the original initial endorsement for the image as authenticated data, right? Or as KDF, then we will be able to generate the same HMAC key, in which case the OS state across reboot, we are able to verify at mount time that this was an OS state which we have seen before because it was signed by our HMAC key, right? So all the security guarantees now here are depending upon the security of the platform itself, which is guaranteed by boot integrity, and the protection around this HMAC key, which is bound to a secret which is owned by that platform, right? And so essentially, just like we were maintaining an integrity chain across the supply chain, we can now maintain an integrity chain across boot and reboot, where on every mount we extract we derive the HMAC key, which is based on a secret owned by the trusted platform, right? Again, the boot components, and the the initial image identity used as the parameter in KDF, right? And so the HMAC key represents both the boot integrity as well as the initial image integrity, and then the signature around the current Merkle represents the runtime integrity, right? And so essentially, what we're saying is the runtime integrity and the signature around the existing hash, we bind it to the initial boot initial integrity, because the initial endorsements are used for the KDF of the HMAC key, as well as the boot integrity, which is represented by this particular seed, right? And so this is the essential primitives in implementation. Both on our Windows and Linux side, the implementations look slightly different because of nuances of each platform, right? But in the raw abstract sort of artifacts, this is exactly what we're trying to do to establish the state. And so if you notice, we have the HMAC key, which is generated at first boot, and then we are using it to sign the root hash Merkle every time we are making edits, and every time we mount, we use it to verify it. We can technically even rotate the HMAC key on every reboot, right? Unlike integrity, where we have block level integrity, where where there's a checksum maintained for each block, and if you decide to rotate any keys, you have to update all the blocks, right? In this case, our integrity for the entire read write is maintained by the read write Merkle and a root hash, right? The root hash has to be signed with a particular HMAC key, and so technically at time t1 we can derive the key for time t0, verify that this is a disk we have seen as part of this platform, right? But now for this particular reboot session and run, we can rotate our HMAC key. Basically, we rotate our platform bound secret, refresh our platform bound secret to a new secret, generate a new key, and start signing their state with a new HMAC key, right? And what this allows us to do is now create some one-to-one binding, which is across each reboot, right? We are maintaining state where each updates are signed by a particular HMAC key. There is one other aspect which I've not included in this slide, which is during one runtime as well, we would like to protect against rollback, right? Where we roll back one disk versus the other. And so we do have a notion of a logical timestamp, right? And the logical timestamp is periodically is incremented for each sort of operations which is performed by our Merkle. And the logical timestamp is also mixed in with the Merkle and its value stored with the platform, right, in the UFI state. And so what that allows us to do is also get some logical timestamp, which is at even during one runtime, if you take one disk and try to roll back that disk by particular time threshold, I think roughly a few seconds, we will detect it, and then we can cause, based on the policy, we can bug check the system or block or notify the customer, right? But so essentially what we're trying to do is make sure that there is one-to-one binding between the OS state and the firmware state across reboots by rotating keys, and then within that particular session as well by using the timestamp counters which I just mentioned, right? And so this is essentially the implementation we put in place. We have a working implementation of this end-to-end running for our Windows scenarios, right? And we are building together with some partners similar scenarios for Linux, right? Again, we are open towards collaboration and discussion, critique, right? Design, collaboration on implementation, right? We are working with distro partners like RHEL and Canonical and Azure Linux. But yeah, we are more than happy to work with others. I do want to maybe complete some of the final details. So again, disk identity and integrity is then basically dependent on the initial image identity, which depends on the authenticity of the publisher, right? Is it a publisher you trust? And then runtime continuity will depends on the authenticity or protections around the HMAC key, right? So these two are maintain the initial image identity and runtime continuity. And then authenticity of the um, this thing which needs to verify the initial publisher signatures or the HMAC key signing has to be done by some trusted entity inside the confidential VM. So for OS disk, we rely on trusted boot components, right? So UFI, UKI, boot manager, right? For Windows, our implementation is largely in boot manager. For Linux, our current draft implementations are all in initRD, though we did find some issues with it, and we had to write a early boot component for some of our POCs. But yeah, work in progress. And then the just one call out is, the system I just described, the HMAC key belonged to one system, right? But for other scenarios, especially data disk like scenarios, we could technically have a HMAC key which is bound to a secret, which can be delivered to a trusted collection of systems. So what that basically means is the data disk from a known identity can be attached to VM 1, 2, and 3, as long as VM 1, 2, and 3 are trusted. And they are trusted. The definition of trust is they have access to a shared secret, right? And so if we attach this disk to a machine 4, right, which does not have access to the secret, one, it will not be able to maintain the continuity. So either it will either not modify the disk, or if it does modify the disk, there will be a new root hash which it can't sign. When we bring that particular data disk back into and try to reattach it to our trusted set of systems, they will not be able to authenticate that disk, and so can deny attach, for example, right? And so we can have disk attach and detach policies, right? And so again, I think essentially what we're trying to say here is, historically for read-write disk, we didn't have a cryptographic identity. Now we can, and now we can use that to drive policies within the confidential VM environment, right? There was a question asked around what the entire boot sequence looks like, right? Again, calling out when I mentioned disk, the disk is a confidential. It's a virtual disk attached only to the confidential VM. So on first mount, first boot, it is basically attaching the CVM, right? The boot components, verify the publisher signature, generate the secret, stored. This is in our implementation, we stored the parts of the secret to which are sealed and stored in a EFI boot variable, not exposed to the operating system environment. We extend the measurements in TCG log, and then we generate the key and HMAC, which is then used to sign all updates to the disk. And then across in reboot, similar sequence follows. But in this particular case, we will try to fetch that particular seed and the publisher measurement which we had stored. Again, derive the HMAC, right? Verify the newly mounted disk. Can it actually be verified? Is it really the same disk which we may have previously signed? If it is accepted. We extend the boot measurements.
We already at time.
Okay.
We still have two hands up. Let's quickly go through them. Probably.
Yeah, let's do that
in a minute. Also, Giri first.
Actually, Greg was first. Yeah.
Oh, Greg, sorry.
I turn it over to Gary.
Okay. Yeah. So Pushkar, really quick, the HMAC key, it doesn't seem to be bound to a boot cycle. I was wondering what happens if there's some sort of interposer attack where on the at T0 after T0 some adversary stores off the data that's being read back by the CVM. I mean, we assume that at initial boot, the data that the CVM is storing on the disk is relatively constant. Then can it, could a adversary go ahead and just replay the HMAC, the HMAC protected data that's being read at cold boot?
So in our scheme, both the OS state and the firmware state, which are both in the backend, virtual hard disk state, which is bound to the confidential VM. The initial boot state, the HMAC which is stored, the HMAC is not directly stored. The HMAC, the secret from which the HMAC is derived, is stored as part of the firmware. Firmware integrity is assumed and guaranteed as part of the firmware implementation of the confidential VM, right? So we have a firmware state. The firmware state is encrypted and entirely integrity protected, and that firmware state is bound to a particular confidential VM. So it's a valid point, I think, to bring across, right? What we assume and what we depend upon. And so what we depend upon here is that the entire UFI TPM state and its protections are intact and guaranteed. Those are being guaranteed by the guest firmware implementation, and that guest firmware implementation is what is measured by the hardware. In the case of SEV-SNP, SEV-SNP measures the guest firmware implementation. So if there is any violation of the boot integrity, where we can, for example, turn off secure boot undetected, or be able to load a malicious boot bugger, but somehow still get access to the sealed secret, right? Because we didn't we didn't do the sealing properly, then those would be all vectors of attack, right? And the HMAC can leak. So any sort of attack which can lead to HMAC leaking can cause an attacker to modify the contents within the disk, right? And that's would be a cause for concern. Even so, I think what we're trying to do in this space in our implementation is, even if the HMAC itself is leaked, the attestation, the way we actually end up storing, right, some of the publisher measurements in the initial boot, if the boot integrity is intact, you cannot attest a malicious OS disk as a good OS disk, right? So if you, for example, if I generate a Pushkar's malicious OS disk, try to boot a CVM and make it look like Giri's good disk, for that I would have to violate the boot integrity. I have to break initial boot somehow, and make sure that the KDF performed during the boot bound to the secrets can be mucked with, which is technically still feasible, right? There could be a boot, UFI bugs and other bugs which exist, but the idea here is that just mere leak of HMAC won't let you attest the system as a different system. But yes, you're right. All the protections here and guarantees are based on protections we can put around HMAC key. In fact, we have a roadmap of, for our Windows solution, how to protect more of that HMAC key as it's used in the lifetime of the CVM to sign updates to Merkle, right? Similarly, what other hardening we can do to ensure that the initial boot integrity, if it's violated, we can detect it and further lose the secret and the HMAC key, right? So there's a lot of hardening work we are still doing in that space.
We're already 5 minutes in. We're already 5 minutes late. Let's probably move further discussion to follow up. And thanks everyone.
Thanks, Pushkar.
Session. Yeah.
Thanks, Pushkar. Thanks, everyone.
Thanks a lot, guys.
Thank you, Pushkar.